Welcome everyone to NSTA web seminars, where you can find live interactive learning at your desktop. Tonight's presentation is part of our series, Preparing for the Next Generation Science Standards, and tonight's focus is on analyzing and interpreting data. Our presenter is Ann Rivet. My name is Bryn Slate, and I will be moderating tonight's program, and we have technical support from Jeff Lehman here at NSTA. I'd like to remind everyone to visit the NSTA Learning Center, where you can find over 9,900 resources for science teachers. Over 3,400 of those are free. You can add them to your library to access when it's convenient for you. And I also encourage you to visit the community forums, where you can continue the discussion on tonight's topic. Also, reach out to our online advisors if you need assistance. They are there to help you and get the most out of your learning experience on the Learning Center. If you're looking for a way to organize and plan your professional learning, do check out our free tools. And it's all available by going to learningcenter.nsta.org. And now I'd like to go ahead and turn it over to Ted Willard, NSTA's Director of Efforts around the Next Generation Science Standards. Welcome, Ted.
Thanks, Bryn. Happy to be here. Happy to have everyone here tonight. I know a number of you have already heard me say some of these things, but I do want to just touch on and make sure that we're all sort of on the same page to get going here. To just quickly go through here that we know the Next Generation Science Standards are an effort with 4 organizations sort of leading the charge. You've got the National Academy of Sciences, Achieve, NSTA, and the American Association for the Advancement of Sciences. And there's a sort of a multi-step process here. We have the K-12 science, framework for K-12 science education that was developed and published back in July 2011, and that's being used to develop the standards themselves, and that effort is being coordinated by Achieve, and 26 states are engaged in the development of those standards. They each have teams that are reviewing them and providing feedback to the writers on how all this goes together. The states in blue there are the ones that are participating, but that the other states also will ultimately have the option of adopting them. So just, even though if you may be from a state that's gray on this map, that doesn't mean that you won't have a chance to use them. And those standards will be used to create assessments, curricula, instruction, and also to guide the teacher education, teacher professional development. So there has been a draft of the standards that was released back in May, and we're now waiting for the second public draft, which is going to be some point later this fall at our Louisville NSTA conference. Stephen Pruitt was there, one of the featured speakers. He told the audience that is expected in either late November or maybe very early December would be the time frame for when the next draft will be released. But I want to emphasize that the actual standards aren't out yet, so don't be looking for materials that address the standards, because you can't address something that's not there yet. Going back to the framework, which is the focus sort of this series, what is established. As I said, it was released back in 2011 by the National Research Council. They had a committee that was involved scientists, including some Nobel laureates and some science educators. There are 3 dimensions to the framework. There are the scientific and engineering practices, what this web series is focusing on. There are also cross-cutting concepts and disciplinary core ideas. If you haven't seen the framework, I really encourage you to get it. You can get a free PDF from the National Academy Press, or you can buy a print copy from NSTA Press. The scientific and engineering practices, one of the first dimensions of the framework, are listed out here. We've gone through our series, the first 3, and we're now on number 4, analyzing and interpreting data. You can see what's coming up down the road. And then there are 7 practices. These are things that more cut across each of the disciplines in science, and the examples that are shown there. And then we have what we're more familiar with as sort of traditional content of science, in life science, physical science, earth and space science, and then new engineering technology being folded in with the traditional science disciplines. And in each of these places you can see the subtopics within these major categories. So here's an example of what Achieve is doing the writers are doing in terms of pulling all of these different elements together, that you have them constructing performance expectations. This statement here, the construct and use models to explain that makes use of a practice. Atoms combine to form new substances of varying complexity in terms of the number of atoms, and that gives you the sense of a disciplinary core idea. And the idea of patterns comes up in terms of repeating subunits that can be done here. And with that sort of as a set piece of sort of knowing how the standards are starting to be created and developed, I want to pass things over to Ann so we can focus on the practice of analyzing and interpreting data. Off to you, Ann.
All right, thank you, Ted, and thank you very much. Good evening, everyone. I am very honored to be here tonight to talk about the practice of analyzing and interpreting data. So a little bit of background on who I am. I'm an associate professor of science education at Teachers College of Columbia University. I have a science background in both physics and earth science. I focus mostly on earth science education now. A lot of my work focuses on the design of learning environments that support students in understanding the earth from lots of different perspectives. And I keenly focus on the connections between curriculum, instruction, and assessment, and the way those three things come together to build learning environments that really promote students in developing robust science understandings. A couple of caveats related to my background that are relevant for this talk. First of all, I was not part of the framework development team. I have been an informed observer of the process, but not actually involved. Also not an expert in engineering or engineering education, although I am going to try and speak to engineering at different points in the talk and bring in some examples that might be relevant for the group. So a quick overview of what I'm going to talk about tonight. The first is, what is the practice of analyzing and interpreting data, and why is analyzing and interpreting data important? Then I'm going to talk about some connections around this practice to other practices that are described in the framework. I'm going to spend some time talking about the progression of the practice across kindergarten up through 12th grade. And in that discussion of progression, talking about lots of classroom examples and what it looks like when students are engaging in this practice. And at the end, I'll have some discussion points, and in particular, try and address some issues around assessing this practice as well. So I wanted to first start with a poll, and just to get a little bit of feedback from you. And so in this poll, I'd like you to respond to the following prompts. Which of the following do you not consider to be data? And Bryn, I think you're going to pick this up.
Yes, thank you, Ann. And everyone, you'll see that your poll buttons are now active. It's right below your own name there on the participants window. And you can select A through E to give us a response. For those who are just joining us, we are just in the first section of our presentation here, and we're responding to a poll question. You'll see that those poll buttons are under your own name there in the participants window, and you can select A through E to give us your answer. We will keep the poll open for a few moments here to give everyone a chance to respond. It'd be great to have everyone share an answer on this one. And it looks like you guys are very fast on the draw here. Most everyone has submitted an answer, so I will go ahead and lock those responses and publish them to the whiteboard.
All right, thank you very much. So as we can see, most people felt that all of the above can be data. And the reason that I asked this question is not so much that I felt you didn't know, but oftentimes when we talk about analyzing and interpreting data, we tend to get tunnel vision around what we mean, focus primarily on numbers and measurements. And when talking about this practice, it's important to keep in mind all the different forms of data with which students can analyze and interpret. And so I wanted to bring that to the forefront and not lose sight of the fact that drawings and photographs and written observations are all really important forms of data as well for students to work with. So what does analyzing and interpreting data mean? Well, let's start with what data is. Data are facts, statistics, or items of information. These are pieces of information that come from objects, from systems, from phenomena, from out in the world that we can use to make sense of things. Analyze is to study or determine the nature or relationship of the parts. So to analyze data means to try and figure out either the nature of that information or the nature of the relationship between different pieces of information from your phenomena or objects or whatever is under study. The interpretation part means to explain the meaning of, and that means of the descriptions of either the nature of the data or the relationships coming out. What do those things really mean? And so in that sense, what it means to analyze and interpret data, it's the process of assigning meaning to collected information and determining conclusions, significance, and implications. So it's a two-part process that scientists and students engage in of both assigning meaning and then determining the conclusions, the significance of that meaning for the question under study. And this is really important because that nature of determining relationships and assigning meaning is a function of both the type of information that's collected, the type of data that you have, as well as the questions asked of that data. So both of those things play into what happens as students and scientists go about engaging in the process of analyzing and interpreting data. So when we talk about the practice of analyzing and interpreting data as put up by the framework, practices are ways of thinking about and working with science concepts to address problems and answer questions. This is more broadly, and all the different kinds of practices that we're talking about in this series are different ways of thinking about and working with science concepts to address problems and answer questions. The goal from an analyzing and interpreting data, the goal of science is to connect information in the form of data to some sort of claim or explanation. But in the process of doing so, you can't just take information and tie it to an explanation. It needs to be put in a form where the meaning of the data can be recognized and extracted. And this is what we mean when we talk about the practice of analyzing and interpreting data, is taking it and connecting this information that comes from some sort of phenomenon or object and connecting it to some sort of evidence that can be used to support a claim or to argue a point. The guiding questions that students should be thinking about as they engage in this practice is, what does the data that we collect really mean? And how did the data help me answer questions? And in thinking about that, the data become more than just pieces of information, but they move towards having meaning that can then be used as evidence. Okay, so why are we focusing on analyzing and interpreting data? Well, the couple of points I brought up before, the key is a key piece of both the doing and the thinking of science that's often overlooked or skimmed over. When you talk about students doing experiments or investigations, they collect the data and they come up with a conclusion. This is not an area that typically has been paid a lot of attention and really needs to be, because it is very complex. It's also a central part to connecting abstract ideas and concrete examples. It's a way that the big ideas in science, those cross-cutting themes, become specific within phenomena and tangible experiences that students have. Analyzing and interpreting data uses multiple tools and strategies. There's no one single way to do it, so there's lots of different ways in which students need to learn how to do and how to think about doing this practice. It engages a wide range of thinking and reasoning skills as well as quantitative and mathematical, as well as more qualitative and holistic. And it has particular importance for engineering in that the iterative cycles that engineers involved with are not just trial and error trying to get it right, but those cycles are about figuring out how their design worked in a particular way and why it worked in that way, so they can use that information to inform the next cycle. So this process of analyzing and interpreting data has lots of different central roles in the ways that both science and engineering make progress and move forward. So how does this relate to the practices that are described in the framework? It's one of the 8 sets of practices that Ted laid out at the beginning. And in a lot of senses, analyzing and interpreting data, it's the process of connecting information gathered in investigations to the explanations, models, and arguments through the transformation of data into evidence. And so if the obtaining evidence is the central purpose that underlies why you'd want to engage in analyzing and interpreting data, in that sense it's connected to all the other practices. And I'm about to describe how. So first, it's connected to planning and carrying out investigation, because that's where the data comes from. It's also tied very directly to how the question is asked and the problem is defined, because that guides the, that informs how what tools and strategies will be used to interpret the data. In the same sense, the data then goes back to inform the question and possibly inform posing new questions as well that could be investigated. The practice is informed by the models of the practice of developing and using models. Those conceptual models go to inform the process by which data is analyzed and interpreted, and the outcomes of this process can go back and inform what models are, and possibly the modification of models or the increased sophistication of models. The practice makes strong use of the practice of mathematics and computational thinking. The two go hand in hand in a lot of senses. And it's key in informing the explanations for different phenomena and the solutions for different designs. It is also key in informing the evidence that is used as students engage in argumentation. And it's key in informing the information that is communicated and evaluated in the practice of obtaining, evaluating, and communicating information. And so in that sense, it's a very central practice to the scientific process and engages all the other practices as well. And most of these couldn't be done to their fullest potential without also engaging in analyzing and interpreting data. So I'm going to turn it over to Bryn.
Actually, I'm going to jump in. Yep.
Ted, before we get started with the questions, I'd like to give everyone some logistical reminders. Ann, if you could turn off your mic for a moment here, thank you. I'd like to let everyone know if you'd like to turn off the notifications of other participants arriving, just to follow the steps here on the screen. In a moment, we will be turning on our chat for everyone to get started submitting their questions and ideas. And if you would like to minimize your chat, you can do that by selecting the downward pointing arrow on the left side of your screen. Or if you would like to make your chat window bigger and see more of the conversation, you can detach it by selecting from the pull-down menu on the right-hand side of your screen, selecting Detach Panel, and then expanding the borders with your mouse. I'll also remind everyone that you can continue the discussion in our NSTA Learning Center Community Forum. I'll be posting the link there in the chat. And right now, I will go ahead and turn on the chat and open it up to your questions.
Great. So we'll have some folks who I think put up some questions here in a moment. But as a starting point, I will throw a question out here. I was noticing that you had a link between analyzing and interpreting data leading into, or how using mathematics and computational thinking fits into analyzing and interpreting data. Would there be a reciprocal relationship in that instance, or is it really just a one-way approach?
I think from a learning perspective, it's definitely a reciprocal relationship, in the sense of, as analyzing and interpreting data uses the tools of mathematics in order to identify patterns and relationships and make meaning of those patterns and relationships. But in the process of engaging in that practice, the notion of what it means to use the mathematics and what the mathematics is really trying to do becomes more obvious and clear. It's like the more practice you get using tools in different ways and in different contexts, you better understand the tool. So in that sense, I think there is a reciprocal relationship between them.
Great, thank you. I'm going to just take a quick one from Jory and Janie about when NGSS will be released. It's basically some point in the first quarter of 2013 is the best we have right now. But I'll go on here to Peter's question. When students analyze data from an investigation, is it reasonable for them to use limited data, maybe from a lab group or a classroom, to formulate a conclusion? Or should they assume that because it is limited data, they should not form definitive conclusions?
That's a really good question, and I'm going to talk more about that in some of the examples I'm going to present. A lot of it depends on context and the ways, what about the data and the kinds of conclusions you're hoping students will develop, the role that that plays in their developing understanding. But I will attend to that question, and if I don't, please come back around to it.
Great. We will try to address that in a little bit. And then I've got a question here from Catherine. She points out she thinks that that this is one of the things that students really struggle with, and actually I think as I read the question, it's something we're going to address further on as well in terms of what are some methods that students could use to improve in their ability to analyze data. And so why don't we go ahead on to the next, to the rest here, and we'll tack on some questions as we go through, and you can show us some of your examples.
That sounds great. Thanks so much. All right. Okay. So before moving on to the examples, I wanted to talk really quickly about some of the tools for analysis. When we talk about analysis, what exactly do we mean? There are lots of different tools that scientists use and students should be using when they engage in analysis. And here's just a list of several categories. The first are tables. Tables are tools because they allow students and scientists to organize data in lots of different ways, and it facilitates the summarization of data in different ways and in very accessible forms. So for example, if you think about an investigation where you're examining, let's say, plant growth, and comparing light and dark or wet and dry, and you measure height and number of leaves over a period of 2 weeks, by organizing the data in a table, you can look across a single variable across time, or you can look at one point in time across multiple different variables. And all of those can be summarized in different ways. It really facilitates that. The second tool are graphs, and there are lots of different kinds of graphs. There are bar graphs and line graphs and scatter plots and pie charts and whisker charts and things like that. What's important about all of these different kinds of graphs is that they provide visual summaries of the data, and they allow the kinds of relationships between variables to be made. You can see things in the graphs that you can't see in just a table. Mathematics, as I was talking about before, is about expressing relationships between different variables in the data set. And mathematics does provide these really elegant and powerful tools to describe those kinds of relationships with a level of precision that you don't get with sort of your generic descriptive accounts of relationships. So for example, if you're talking about the relationship between mass and acceleration, it can go faster and faster. That doesn't give you enough precision, but when you put it in an equation, then you actually have a, I think I said the signs wrong on that, but between force and acceleration, you actually have a more precise description of what that relationship is. Computer-based visualization tools, there's all sorts of different kinds. Map-making tools like GIS tools and Google Earth, those are one example. Dynamic models are another kind of example. plots of things that create visualizations of differential temperatures or compositions or in fluids and things like that. Those are all the kinds of visualization tools that allow data to be put into a variety of different forms. And many of these tools, and I'll talk about examples later, allow data to be displayed in multiple different forms simultaneously. So out of one tool, you can get a chart and a graph and a map. And using all of those together, then you can conduct your analysis. The last tool is standard statistical techniques, such as mean and mode and variability and correlation. Those help to both describe relationships in the data and help to understand and reduce the effects of error in the interpretation and in the analysis interpretation, and help students and scientists recognize where the error may have come from and how much confidence to have in that interpretation. So those are the different tools. When scientists are looking at data, what are they looking for? They're looking for all sorts of different kinds of things. They're looking for patterns in the data. They're looking for significant features, such as spikes or drops. Or they're looking for relationships, things that seem to go together all the time. They're looking for trends, things that seem to occur continuously over time, or increasing at or decreasing at particular rates over time. And they're looking for anomalies, because anomalies might also tell you something about the where the data may not be matching what the expected outcome should be. So those are all things that scientists pay attention to when they're looking at data, and all of these are things that scientists should, not scientists, students should pay attention to as well when they're working with data. So really quickly, I want to stop and take a quick poll, another poll, and ask the question of the group: how often do students work with data in your classroom? So, Bryn?
Thanks, Ann, and everyone. It looks like most of you are already on this one very fast. But if you are not sure where the poll buttons are located, look at the top of your participants window under your own name, and you will see a button that has an A on it. And if you hold your mouse over that, you'll be able to select A through E to give us your response. And please do use your poll buttons to respond there, because it will be tabulated in our graph that we'll publish to the whiteboard here. If you have typed it into the chat, please do go ahead and select an answer from the poll button itself, because we would love to have you included in our results that we'll publish on the whiteboard here in just a moment. And if you're just joining us, we are responding to a poll question here in tonight's program. And your poll buttons are located at the top of your participants window, right under your own name. It looks like we've got a great response rate so far, so I will give you just one more moment if you haven't yet had a chance to answer. And another 15 seconds. And now I will go ahead and lock those responses and publish them to our whiteboard so that Ann can see the results along with all of us. And back to you, Ann.
Thanks so much. This is great. Thank you for your feedback. So as you can see, a lot of people provide lots of opportunities for their students to work with data in the classroom, which is fantastic. So using this information in context, I'm going to talk about what it looks like when students are working with data at different grade ranges. And what I'm hoping is that through the different examples I'm providing, that you will be able to see opportunities where your students are or could be working with data even more and building their expertise with this practice. So thank you. So when the framework is talking about progression of the practice, they're referring to students increasing sophistication and fluency of the practice across as students move through K-12 science. And what's important, the important distinction is that by increasing sophistication and fluency, they're not talking about more opportunities. What they're talking about instead is a change in the quality of how students engage in the practice. So in this sense, lower school students would engage in simpler aspects of the practice as they begin to learn the basics of working with data and how to interpret and how to analyze. And as students move through the grade, their work with the data becomes more robust and more technical, with increasing uses of quantitative approaches, more complex tools, and more challenging relationships. So let's start in the lower elementary school. For analyzing and interpreting practice at this grade level, the focus is really on collecting, recording, and sharing observations. So in this sense, students can record and share, both verbally and in writing, things that are tangible and very present to them, such as growing plants and the weather and things like that. They can make all sorts of different kinds of measurements, measuring things starting with measurements that are relative to other objects, such as things like size, pumpkin solved, and then move to doing more quantitative, more standardized units, such as how big are things in centimeters, or how much do they weigh in grams and ounces. They can note patterns and relationships. They can make tables and charts and graphs of their observations and begin to see the kinds of common things that show up over and over. And in doing these things, at this grade range, students are building the foundation for taking information that are gathered as data and organizing it to look for relationships and then giving meaning to those relationships, which is really the foundation of the practice. Now, as students move to upper elementary school, the emphasis moves to more quantitative approaches, beginning to work more with numbers and measurements, and with multiple trials of qualitative data, so beginning to get to this notion of evaluating. Students display data in tables and graphs more and more. They compare data across different groups to begin to look at the notion of multiple trials. And they begin to attend to claims of cause and effect and whether or not the data are supporting claims of cause and effect in their investigations. So to talk about this, I'm going to present one example, and this is a upper elementary, lower middle school example of a project-based unit in which students are investigating force, motion, and simple machines. In this particular set of investigation, students are looking at the advantages of machines and examining the question, how can machines move things that I can't? So it's a 3-lesson sequence. And in this lesson, students are trying to figure out the relationship between how much force it takes to lift a brick to the top of a pile of books, as opposed to moving a brick using an inclined plane. And they're measuring force, but they're also measuring how far they have to apply the force to, how far their hand moves. So in this first lesson, looking at the inclined plane, each group takes one measurement of force and distance for each one of these different setups. And then the group measurements are pulled into one class data table, and there's a class discussion around consistency and identification of outliers. And this begins to get us a notion of precision. The teacher models how to average the data and how to create comparative bar graphs. And through discussion, the class generates an interpretations of the analysis of this relationship, which is not showing up very well on the slide, by developing an initial class rule for the relationship between force applied without an inclined plane versus force applied with an inclined plane, and the relationship of the comparison relationship with respect to distance. The second lesson in this example is students' investigations of levers. They have a similar setup where they're measuring the force needed to lift a brick to a pile of books using their hand, and using a lever, so the brick would move up here as they pull down. Again, they're measuring force and the distance they need to apply the force. Similar to the previous example, each group conducts one trial of the setup, gathering for both force and distance data. The data from each group is again compiled in data tables. However, the groups then work individually in their small groups to average and graph the data. So some of the scaffolding has been removed. They share and compare the graphs, and the class writes interpretations. And these revise their initial class rule around the relationship between force and distance. And the third example in this, the third investigation in this set, students are investigating pulleys, both fixed pulleys and free pulleys. So again, they, in this case though, they're conducting 3 trials of each setup and averaging their own data and creating their own bar graphs. So the graphs, because they have 3 setups, this is a fixed pulley, this is a free pulley, you end up with graphs that are more complicated and show a slightly different relationship. In this sense, the graphs are then compared and discussed, and the groups write their own interpretations of the graphs. The class then comes together as a whole to interpret that and revise the class rule. So you can see in this example where the scaffolding around how you work with data in larger data sets, what does it mean to average, what does it mean to look across graphs, what does it mean to compare graphs, is supported in such a way that students are building that expertise around the analysis and interpretation. So as students move into middle school, the emphasis moves to increasing quantitative analysis and investigation, distinguishing causation from correlation, and the beginnings of basic statistical techniques. And by statistical techniques, they're talking about things like mean, median, mode, and variability. These are concepts that are emphasized in math class and are brought into the science classroom to work with quantitative data. They also begin to identify the differences between linear and nonlinear relationships in graph form. So what does it mean when you see a graph that's a line versus a graph that's a curve? They begin to consider limitations such as measurement error and ways to increase precision. So as much as the previous example used multiple trials, in this case students are beginning to understand why that's so important. And they're looking at graphical displays of large data sets to analyze temporal and spatial relationships as well. So I have a couple of examples here of this. One of these is another example of a project-based science investigation that's around investigating motion. In this case, the students are trying to understand the question, why do I need to wear a helmet when I ride my bike? And it's looking at concepts of the relationship between mass, velocity, acceleration, and force. So students in this example are using motion probes to first look at the characteristics of distance time graphs and noticing that these are different motions moving away and towards, slow, medium, fast, medium, and slow, fast and slow, fast and slow. But what you can see in the graph and what students are noticing is that what matters is the characteristic slope changes and the direction of the slope matters. And that is correlated with the kind of motion that they have. They then use this information to interpret velocity time graphs to examine acceleration. And they investigate how accelerating down a steeper graph results in, or moving down a steeper ramp results in different kinds of acceleration. But when mass is increased between light and heavy mass in the cart, that has no effect on the acceleration, and you can see how these graphs stay the same. So in looking at these kinds of analyses of graphs, they're able to investigate. They're pulling on a different set of tools in order to conduct this analysis interpretation of the motion data. A second example for this is around a project called Investigating Earth Systems, where students are looking at spatial data. In this case, this is using a tool from called Mapmaker from the National Geographic Society to compare amount of annual precipitation and population to explore, in this case, the question of where is all the water. And in this instance, students are looking at relative mean population density to the amount of precipitation and comparing that to averages. So the greatest precipitation is also located in places with the highest, some of the highest population density, where places that get less than 10 centimeters a year have very low population density, which you can see this is low precipitation and low population density, such as in the Sahara Desert and some of the mountains. The point of this investigation is not only to begin to look for these patterns, but to understand how the usefulness of the tool allows you to look at patterns across the Earth and allows you to see data in ways that you couldn't see it before. In high school, as students move into 9th to 12th grade, the practice becomes more robust. It includes more computational mathematical models. Students are considering limitations to the analysis, such as sample size and measurement error. They're looking at how different mathematical functions fit to data, such as slope and interslope and correlation coefficients and what they mean. And they're looking at triangulating data across different data types to examine consistency of measurement and observation. I have a couple of examples of this as well. The first is a water quality investigation that students conducted outside of a stream that was outside of their school. And in this case, students are collecting visual images in the form of using a digital camera, along with quantitative data, including pH, dissolved oxygen, turbidity, and things like that. They're analyzing all this data through tables, graphs, and comparison of images, along with archival data, in the fact that this class has been examining the water quality of that stream outside their school for many years, and students pass the data down from year to year. And in doing that, students are able to look not only at what is happening in their stream at that time, but how it's the same and different from previous years. So this is really emphasizing the practice of triangulating interpretations across multiple data sources. Computational models begin to become present in middle school and high school. This is an example of the Educational Global Climate Model, the EDGCM. And this is an educational version of the same global change model that scientists use in order to study climate change. In this version of the tool, students set up different criteria, and output comes in lots of different forms. There's visual output in terms of plots, you get data tables, you get comparative graphs, and it begins to ask students to engage in looking across all these different factors and variables at what causes what and what is the nature of the relationship between those different variables. Similarly, there's a program in engineering called Engineering Energy Efficiency that engages students in multiple different kinds of tools. This is a CAD design tool to design houses that are then tested using a set of lots of different kinds of instruments. This is a thermal sensor where students are measuring the thermal output from their model house. So in studying the question of how do we design an efficient solar house, they're designing and testing houses to improve the efficiency using lots of different tools, but they're also they're drawing on very substantive science content, including power, energy, heat transfer, thermal equilibrium. All of these concepts are needed in order to understand both how to design and iteratively redesign their prototypes and how to make sense of the measurements that they're taking with the different technologies. So I'm going to pause here for questions, because I know that was a lot.
Thanks, Ann. And before we do open up our chat again for your comments and questions, I wanted to remind everyone that you do have the option of turning off those notifications of other folks joining by following those steps there on the screen. You can also minimize your chat window by using the downward pointing arrow on the left, or detach your chat panel and expand it by using the pull-down menu on the right. And I will remind everyone to continue the discussion there in the community forums. At this point, we will open up the chat again and encourage your discussion and questions. And Ted Willard will be bringing back a few questions that were submitted while Ann was speaking.
Great. One of our first questions, Ann, was asking about some of the materials you showed in terms of the activity with the block on the incline plane and measuring things. If you have a reference that you can give folks of where they could find a copy of that activity or description of that activity, and that might be something that you could either post up on there later in the discussion when people go and have their are filling out their review of their survey of the entire course, the workshop. The next one was I guess a few more specific questions about that. Was the materials you showed, was that a free, or was there a cost for that material, or was it a freely available material? And also interest in whether the educational global climate model is an online tool, or whether it's some software that you have to buy.
Most of the materials that I put out are, I believe, freely available. I think some of them are published either in the Project-Based Inquiry Science series. The Investigating Earth Systems materials it's a published series, but the map-making tool, like the pre-GIS tool, is freely available from education.ngs.org, I think, from National Geographic. The Engineering Energy program is still in prototype phase, and that's free. What was the last one that I was asked about? The global climate change model. I think that is not free, but there are.
All right, let's go on to another question here. Someone's asking for younger students, the elementary grades, K2, 3, 5, which is more important, what they can see, manipulate, or what they can mathematically manipulate?
In terms of analysis? In terms of analysis, it's about, in particular at the younger grades, it's more about the reasoning process than the actual mathematics. And so when you start in second, third, fourth grades, fifth grade, around there, the connections between the conceptual ways in which relationships are articulated and the mathematical ways in which relationships are articulated, it's important to begin to develop that, and so students can see how the tool allows you to describe things that you could describe in words. And so both are important, but if all you're doing is the mathematics without really understanding what the mathematics represents in more conceptual terms, then that doesn't make a lot of sense for the kids. And they're doing it without really deeply understanding the process behind the practice, or the rationale behind the practice. And so in that sense, it's more important for students, first and foremost, to have experiences that allow them to develop the thinking and reasoning behind analysis and interpretation before they begin to work with the mathematics. Although the mathematics should, as a tool, help them to further deepen and increase their fluency with thinking about those kinds of relationships.
Great. I'm going to knock off a few specific NGSS comments here. Peter's asking about whether NGSS will have specific activities suggested as shown as examples here, or will teachers need to generate these activities? As someone else is putting out, the NGSS will be a curriculum, or will not be a curriculum. It's just a set of expectations for what people will need. The exact form of how clear they will be in terms of providing examples of what's to be expected at different levels is still, I think, somewhat up in the air in terms of what form it could be. And when the public draft is released later this fall, you may want to make suggestions about what you as educators would like to see the standards have in terms of providing guidance. Again, keeping in mind, the tension between providing guidance and also mandating different pieces here. Leanna has an interesting question here. She says, I teach at an alternative high school. Many of my students do not have a background in graphing, interpreting graphs, etc. Can you suggest how to build this background with limited time?
Oh, that's a great question. Graphs are tools, and so what I would encourage you to think about are ways to help students represent the ways that they would reason about different kinds of relationships, a one-to-one linear relationship, or a two-to-one linear relationship, or a exponential relationship, things that go faster and faster, or things that increase at a steady rate, and things like that, in some sort of picture form. And in that sense, develop ways of trying to get them to more intuitively make sense of how the graph represents concepts and relationships between things, and then start talking about the structure, talking about how important it is to have what the x-axis means and the y-axis means, and the different kinds of units on different sides, and what the numbers mean, and the grids. The intuitive piece first helps it become less of a drawing pictures without understanding what it is that they're supposed to be talking about. And the other way that I've seen that works really well with helping students develop in sort of more implicit senses of graphs, in particular line graphs, has to do with having them work with probeware that does real-time data collection, such as or motion probes, force probes, temperature probes, where they can see the data showing up in graph form at the same time that they're seeing a phenomena change. And making that one-to-one correlation between I can watch the change happen in front of me and I can see the representation on the screen at the same time helps to deepen that sense that the graphs actually have meaning in the real world.
I'm somewhat reminded also, to add on to that, the idea of how the practice of analyzing data also works with the practice of planning and carrying out investigations, and to the extent that you want, and I think this is sort of what you're pointing to, having students collect some data so they have a sense of what that data really means is very important in being able to then turn around and interpret that data later, whether or not they are the ones who collected the specific data. Would you agree with that?
Absolutely. That's a really good point.
Great. And then there are a couple different points here I think that sort of fit into this piece of when is the appropriate time to start using certain types of statistics. Someone else has asked about is, I'm sort of lost in the mix here as the screen is scrolled through. Is it okay to do mean and mode at 5th grade? I'm guessing that what we're dealing with here is a progression that we want to make sure students go through, and when they're, and different students will need it at different times. It's not just to try to teach them something if they're not ready for it, or wait if they are. Is that
right? Right, and the idea is that it's the notion of these tools, in particular the statistics and mathematical tools, is that you don't just learn them once and then know exactly how to use them all the time. you learn what they are and what they mean and how they're used by using them multiple times. And so the first time, even introducing them when the notion of average might not make a lot of sense in the abstract, but the notion of figuring out, okay, if you have a high number and you have a low number, well, let's take the middle of that because that's fair. And working with that notion at a very young age and then building that sophistication around what it means to average or take a mean or to look at variance and things, and using those tools over time is really important.
Great, and I think you're hitting in some ways on a question that Allison has asked here about is analysis interpretation of data powerful as a single lesson for student learning, or should we, as educators, always be aiming to use and return to data over longer time periods, as with water quality example or the stream study?
In my view, it's something that should always be going on in the classroom, and it becomes part of what students do when they do science. And so it's not a separate lesson. Today we're going to learn about what it means to look at spatial relationships. Like it's instead about how this practice relates to all the other practices that relate to developing all those disciplinary ideas and those cross-cutting themes, and how it all comes together to do and think about science. It's a core piece that can't be left out, but on the other hand, it's central to how scientists think about and do the work of science, but it's not the only thing that they do, and it's not even the most prominent thing that they do. And so it should be part and parcel of everything that goes on in the science class.
Great. I'll just tackle this one more piece here of Elizabeth asked about who has money for probes. I think this is, the whole issue of funds for science equipment is obviously a huge challenge at all areas and across the country at all grade levels. Teachers I've talked to point out that while trying to do this in a systemic way is often very difficult. If you are a teacher and you really feel that this is something you want, a lot of teachers I've talked to say that they found grants or they found, donors choose or other elements of ways, local businesses. If you can really point to a very specific piece of equipment that you need, even if within your school system your principal does not have funds available, or that reaching out to the community, to parents or things like that, to local businesses, are very often willing to provide some assistance, some financial assistance in doing that. It's not the way that the system should be, but it is a way for individual teachers who unfairly sometimes have to go out and find their own materials, sometimes do have success in doing that. And so that would be my suggestion to those of you who are feeling that's a major obstacle for you. It's not again, not the way the system should work, but the way that it can sometimes work to get what you need to help your students. Let's go on to our next pieces here.
I'm sorry, Ted, you want me to keep going?
Yes, I was going to say let's move on here, and then we'll have a little more question time here at the end to pick up any other questions that folks have.
All right, I'll quickly move through the end. I wanted to highlight a couple of really common challenges that students have with analyzing and interpreting data. The first is under-analyzing the data, and that they connect a claim to a question irrespective of the data. They know what the answer is supposed to be, and they totally ignore the whole data process and analyzing data piece in the process of supporting their claims. Another challenge that a lot of students have is over-analyzing the data, and that one data point does not make a claim. Hey, I found it with one piece of it. Students also have a really hard time with awareness and accountability of errors, so they don't realize when there could be something funky happening with their with the data, with the analysis, and what that means in terms of their interpretation. This notion of precision of measurement, of multiple trials, of accounting for errors, and how that makes you more or less confident in the interpretations that you're making of the data is a point that students really struggle with. The third is the selection of appropriate tools and procedures to analyze the data. Students have a tendency to only pick one way of looking at the data when for most questions, more than one analysis is needed really to address that question. And so helping students engage in looking at the data they have using lots of different tools and using lots of different perspectives can help them develop more robust understandings of the question that they're trying to address. I wanted to briefly address the issue of assessment and what does it mean to determine how students are progressing around this practice. And the goal that I want to emphasize is that it's not so much the technical aspects of analyzing and interpreting, but it's really about the awareness of the relationship between data, questions, analysis tools, and concepts that should serve as a focus for assessment. So I've come up with a few different categories of questions that would be the kinds of things you'd want to look for in the way students are engaging in analyzing and interpreting data. The first is asking students to explain their process. How did they get to that interpretation? And this will, what tools did they use and why? So the second question is ask students to provide a rationale for the analysis tools and approach they use. So what is this why piece? Why did you choose that kind of graph? Why did you do an average? What are the other things you could have looked at, and why did you select this way? So you're looking at students' awareness of the fact that there's a reason why you're analyzing the data, not just because all scientists take averages. It's the average allows you to do particular things. And not all, they're not entering because, well, yesterday we did line graphs, so I need a line graph. No, well, the line graph tells you something. What does it tell you, and why are you looking at it that way? And the third category is around asking students about other considerations during analysis. What could be sources of error in your investigation, and how confident are you in these findings, and what might have made you unsure? And helping them attend to and raise their own awareness of the fact that not all measurement is perfect. Even though you measured it, just because you measured it once doesn't mean that that's the exact right thing. You might have done it, there might have been some error in there, or you might have done some math wrong or something. So what are the places where students are reflective enough on their process that they can identify those challenges? So in conclusion, just a couple of key points. In looking at the practice of analyzing and interpreting data, it's really critical that kids must work with data in order to develop this practice. There's no other way around it. And so, again, as most of you who responded in the survey say that your kids work with data a lot, which is great, and that needs to just keep up. And the focus is on the connection between the question, the data, and the claim. The statistics, the graphs, and mathematics are tools for analyzing the data, not the goal. And so it's really important around the rationale behind the reasoning behind the practice rather than the skill of the practice. This practice is really complex and must build over multiple supported experiences across years. This is not something that can wait until high school for kids to figure out, and it's not something that can be taught in 1 or 2 lessons. It's something that is continually developed over time. And lastly, there's lots of potential applications for this practice across the science curriculum. This is not just a physics practice. This is a practice that can be done in life science and physical science and neuroscience and engineering. All sorts of different concepts and big ideas can lend themselves to students working with data and analyzing and interpreting those kinds of relationships in many different ways. So I want to thank you for your time. I really appreciate it, and I'm looking forward to your feedback.
Thank you so much, Ann. And before we move on to some concluding words from Ted Willard, we will open it back up for folks' final comments and questions. I'll go ahead and turn the chat back on. And we welcome your thoughts and ideas as well as your questions for Ann. Feel free to type those in now.
So before we get started with some of the questions here, I was just reflecting on some of my own teaching experiences here and was thinking about your point, how important is it students to work with the data, and how in some cases where answering your early question about how often you have students interact with data and things like that, I probably answered higher than I probably should have, because there were times where I would present data to students and show it to them and have them, in some cases, think about it, but not engage in the way you're talking about it, really think about how should this data be graphed? How should students themselves wrestle with it? What's the best way to do it? What are the paths in thinking through it? And that I was, in some cases, taking on those responsibilities for them, and just basically trying to present it to them, or having them do some labs a little bit too cookie cutter, or cookbook, I should say, in engaging with this. And the points you're making here are resonating with me in some important pieces here. I'll let you react to that while I grab some questions.
No, I think that's a really good point. It's in the...
And so, Ann, would you have any recommendations, this is from Gary, about grade band appropriate pre-assessments to determine students' data analysis skills? That's a tough one. I'm not familiar with any, but you might.
I'm not familiar with any existing ones. One of the things that I might recommend as a pre-assessment is to, when they're planning their investigations, have them specifically plan an analysis plan. So not just what data they're going to collect, but how are they going to analyze it, and why are they going to analyze it that way, and use that as a pre-assessment before they start collecting their data, to talk about, to think about what kinds of supports you might need to provide in order for them to successfully complete that investigation.
Great, thank you. How should we help current elementary teachers embrace this and other practices of teaching science?
Well, I think that there's a lot of things that elementary teachers do or could do where this practice would fit in really well. And I think that part of this is helping teachers, elementary teachers, see that the writing and the talking and the observing and the describing and the organizing ways of thinking about analyzing and interpreting data at the elementary level are not really all that different from the kinds of skill sets that they're already promoting in their classrooms. And so finding more opportunities for students to write about patterns of things that they see in terms of heights of different kids in the class, or weather outside over the course of a month, or what the moon looks like, or things like that. There are opportunities to integrate it in with what they're already doing, so it's not something additional, and yet at the same time can tie to both the science that they're teaching as well as the other subject areas that they're focusing on as part of their curriculum.
Great. I see a few comments here about claims, evidence, and reasoning, and want to point out some little promo that we will be having Kate McNeil talking in one of our later web seminars specifically about that in terms of developing explanations and engaging in argumentation. Both actually she and Jed Kraychek will be doing those two sessions. Going to a question here from Keith. I have a hard time communicating the concept of making, oh, I'm sorry, that actually was just a piece I was just referring to. Are you aware of any resources that might be useful for special education students when it comes to analyzing data?
I'm sorry, I'm really not. I'm trying to think. Yeah, no, I'm at a loss in terms of that one. I'm not the right person to ask.
Yeah, I think it's, again, the piece that I would think could, the only thing, piece of guidance I could think to provide is, again, thinking about the progression that exists there of what are students at earlier grade levels being expected to do, and working with students to make sure that they have each of the steps in that progression before trying to teach them a particular level. And so the importance of pre-assessment, and then for special education students, that may be an important piece in terms of going and filling in. But I think this points out how the next generation science standards are going to require a lot of new resources for teachers in pulling together and addressing different audiences and student population. All right, next here. Let's see in here. I have some comments here. Michelle has an interesting question here. Do you have any suggestions for getting students to analyze from more than one interpretation without totally relying on the teacher to make suggestions? So, students, frequently their first idea is the idea that they want to stick with, and if you have ideas about how to shift them from that approach.
Oh, that's a really good question. I guess my first thought is to have student groups compare their interpretations with each other. And again, this gets back in some ways to the other practices of explanation and argumentation, but to think about, given a set of data, what are the different ways to analyze it, what are the different interpretations that could come up with, and have them compare with each other. An alternative is to say that to help the students break down the questions that they're asking of the data, and have them look at the question and see more specifically, is this question really answerable with only one approach to data analysis? Most questions are not. Most questions, you need to do a few different things and then tie them together and across interpretations in order to be able to address the question. And so paying more attention to what the question's really asking, and having them ask robust questions of data will help to address the notion of only doing one stab at the data and saying, I'm done. Great.
Elizabeth asked a question here of how do I include investigations that use data when my standards are primarily based on the recall of facts and I have very limited time. A double-edged sword here I'm going to throw out as a starting point in here is that there's always, for any particular fact in science, there's the aspect of how do we know that took place, and then helping students on that journey of understanding that, which leads into a lot of what these practices are about and what the next generation science standards are all about. Is I think a good starting point. Do you have some pieces to add to that, Ann?
That's a really good starting point. So why do we know this? And how did we come about it? And the other piece of this is to think about, rather than teaching all the content and then having students apply that content to, or to use it in analysis, having them do investigations and analyzing and interpreting data as a way to build the content understanding. And developing the kinds of conceptual, the broader conceptual explanations that cut across different kinds of investigations. It's in some ways, unfortunately, a real retooling of the curriculum, but on the other hand, it allows for, what are they trying to say, opportunities for students to wrestle through the content, and in some ways provides opportunities to cover as much content by exploring interesting questions through data than it would take as much time just to simply explain the concept.
What I'm reminded of in terms of you're talking about that is this idea that you're going to give students an understanding that it's going to much more likely to stick with them than just memorizing a bunch of rote facts, and you're also giving them some better skills to work with.
Right.
All right. I think we'll I'd like to now jump into just a few other pieces of where you can find information about the standards, but Ann and I will stick around here and try to answer some further questions on the chat after we go through all of this, and you have a chance to fill out your survey. I want to point out your main place to find some information about NGSS is at the NSTA website, the nsta.org/NGSS. You can get to. There's just a nice, easy link right on the main NSTA web page if you just want to try and remember to do it that way. As you know, this is our continuing series. We'll all be back here, hopefully, same bat time, same bat channel on November 6th. That's Election Day. And so please vote, and then please come to our web seminar. We'll have Robert Mays and Brian Shader coming and talking about using mathematics and computational thinking, and some information there about all the different elements that you'll learn. This obviously will follow up nicely on what we've been talking about here with tonight's web seminar about analyzing data. Mathematics comes into play in a lot of different ways, as does computational thinking. I want to remind folks that graduate credit is available from Shippensburg University for attendees of these web seminars. You either have to actually attend the live presentation and get your certificate, or you can complete the reflection questions. Those reflection questions will be available alongside on the NSTA website, along with the archives of the web seminar. As has been mentioned, we have in the NSTA Learning Center a community forum specifically around the next generation science standards, and a good place for a number of different conversations about what's going on in these web seminars. I hope some of you were able to attend last week the NSTA Regional Conference in Louisville, Kentucky. We've got next week coming up in Atlanta, the area conference, and later on, first week of December in Phoenix, Arizona. I'll be attending both of those conferences and actually doing sessions on the practices, so I hope I have a chance to see you down there. We'll also be doing some sessions about conducting a review of the standards or how to make use of the standards. Take a look at those. A number of sessions that are around the standards that you can take in. As I pointed out, you can get the framework or also a reader's guide that NSTA has presented about the framework. We've also been having a number of articles in our journals continuing throughout this school year about the standards and the framework. And we're very happy to have the support of the Carnegie Corporation of New York to carry out these pieces. And so I'll thank you all again for being here tonight and turn things over to Bryn for the closing words.
Thank you, Ted, and I'd like to thank both Ted Willard and Ann Rivet for their time this evening. We really appreciate all the fantastic information, examples, resources, and I'd like to thank everyone for participating and sharing your questions and ideas. Let's go ahead and use our emoticons button to give a round of applause. It is the button there on the furthest left side. If you click on that, you'll be able to click the applauding hands to give your applause. Thank you so much, everyone. And I would like to thank the sponsor of tonight's web seminar, the Carnegie Corporation of New York. A thank you to the administration of NSTA for their support for web seminars. And I'd like to let everyone know about the upcoming programs on our web seminar schedule. Tomorrow evening, there is a program in our NASA Explorer School series called Pythagorean Theorem, Exploring Space Through Math, Lunar Rover. And then on the 25th, you can learn more about the NSTA Learning Center, free professional learning resources for educators. And later that same evening, on October 25th, another in the NASA Explorer School series, Meteorology, How Clouds Form. And you can register by going to learningcenter.nsta.org/webseminars. Thank you everyone for your participation, and we look forward to seeing you on another web seminar soon.